All right, guys, I am here. Okay, so here's what happened. I just could not log on my internet. So I sent you an email to please wait. And then 10 minutes later, I'm still working. I had to call my internet provider. There was a jam. I don't know why. So still didn't work. I had to go and exchange my internet tower. So I'm gonna post the video, and I told you not to wait on me to go by your own business, by your business, not to worry about it for today. But I will make a video. So now I figured everything out, and I will be getting a fiber internet, Wi-Fi in the next few days. But for now, I have a new tower, so it seems to be working fine, and we are recording the thing. Something happened last time. Nobody told me about it. Remember this example we did, and we ended up being wrong. So there is an X here, and there is a Y here. And then this would be then this would be um, this here would be one. And then everything works fine. Okay. So I just copied the problem wrong from the book. That's all I did. All right. And then everything is fine. Any questions? All right. I don't expect anybody. I am really shocked that I have two students online. I don't know why you guys waited. So, because I did send an email. All right. So now let us go back to let's go back to the pendulum problem. Pendulum problem. After we linearize it, we had x1 prime equal x2, x2 prime equal minus g over L, sine x1 minus b over m, x2. Did we do this example last time, by the way? Yes or no? When we looked at the equilibrium point. I was just going to keep it on to see if you got on. Then I forgot to log. Oh, well, good for you. Anyway, and you will see that a plus or minus n pi 0 or n pi for n equals 0, 1, 2, and so forth are equilibrium points. Okay? I think we did. I have the feeling we did this last time, didn't we? Then J is del F1, del X1, del F2, del F1, del X2, del F2, del X1, del F2, del X2. And that is del F1, del X1 is 0, 1, del F2, del X1, del F2, uh, del F2 del X1. Del F2 del X1 is minus G over L cosine X1 and minus B over N. So J at 0, 0 is 0, 1 minus G over L minus B over M. And if you look, so we're going to have the eigenvalues are minus lambda times minus B over M minus lambda plus G over L equals 0. This is the equation for the eigenvalues. Or we're going to have lambda squared plus B over M lambda plus G over L equals 0. All right, so lambda equal to B over M plus or minus square root of B squared over M squared minus 4G over L, and this is 1/2. Okay? So that is 1/2. So if we write them as, if we write lambda 1 is B, this is minus, sorry. Is minus B over 2M and plus 1/2 the square root of G squared over M squared minus 4G over L, and lambda 2 is minus B over 2M minus 1/2 G squared over M squared minus 4G over L. Okay? So this is where we have all right. So if we if B squared over M squared minus 4G over L is less than 0, then real parts of lambda 1, lambda 2 are negative, and 0, 0 is asymptotically stable. Okay? So basically, this is stable spiral. All right? So this is weak damping. So this is weak damping. So if B squared over M squared minus 4G over L is bigger than 0, over damping, then, and so that is, or B squared over M squared is bigger than 4G over L. Okay? And then so we'll have lambda 2 less or equal lambda 1. They're both less than 0. So 0, 0 is asymptotically stable. Okay. You can verify the other condition on G and show that the condition on G is satisfied. Now let's take a look now. Okay, I'm gonna turn this around in a little bit. All right, any questions? Now let's switch back to, so let's take the equilibrium now. Let's take pi 0. This is for n equal 1. That means x1, and this is x2. So what is the Jacobian? The Jacobian is 0, 1, and for n equal 1, cosine pi is minus 1, so this is g over L, and this is minus b over m. Okay? And then you're going to have minus lambda times minus lambda minus b over m minus g over L equals 0. And this is going to be lambda squared plus b over m lambda minus g over L equals 0. So lambda is 1/2 minus b over m plus minus square root of b squared is b over m squared, b squared over m squared plus 4g over L. And then since b over m is less than square root of b squared over m squared plus 4g over L, we see it's unstable. Okay? This is never gonna be negative. So, and this one is always true. So you have one positive, one negative. So you have lambda 1 less than 0 less than lambda 2. So that's what I mean. One eigenvalue is less than 0, one eigenvalue is bigger than 0. All right, any questions? All right, I think I'm gonna move on to limit cycle. I will be flipping the board very soon. So look at this for a second. See if you have any questions. All right. So now I am gonna be on section 6.4. Limit cycle. Well, sometimes we will have curves, solution that stay on a curve. So sometimes, let's say we may have this in the equilibrium point, and we have, let's say this is x squared plus y squared equals c squared, and we have any solution starting here, it will go to this, it will go to this, or any solution starting outside will go to this cycle. So in this case, x squared plus y squared equals c squared is a limit cycle. Okay? Or a curve that is asymptotically stable. So we're going to look for limit cycle of differential equation p of xy, y prime equal q of xy. Okay? And this is 6.4.1. All right? So definition, and this is 6.41, a limit cycle of 6.4.1 is a closed curve and no other solution that is closed curve exists in its neighborhood. Okay? Okay. So every trajectory spirals or approaches the limit cycle as t goes to plus or minus infinity. Okay? It is hard to determine if a differential equation system has a limit cycle. The next result However, the next result tells us if the system if the system does not admit a limit cycle. Okay, so this will tell us if there is no limit cycle, but it doesn't say there is a limit cycle. So we're going to be talking about it in a second. Go ahead, copy it down. I'm being sloppy, a little bit exasperated with my internet company and trying to go pick up a new tower and set it up and everything. I was really frustrated. So it still shows on me a little bit. Sorry about that. Just let me walk away from you for a minute. You copy the board. Let me know if you have any questions. Okay. Somebody has a question. We did this last semester, but I don't think we did it. We did this last time. Okay. All right. Thank you. So this is called Theorem 6.4.1, Bendixson, Dulac, theorem. Suppose the first derivatives of p xy and qxy are continuous on some closed subset u of R2. If del p over del x plus del q over del y does not change signs on u in u, then system 6.41 has no closed trajectory or solution in U. Therefore, no limits on periodic solution. Okay. So go ahead and read the theorem carefully. See if you have any questions. All right. Here's the proof. The proof depends on Green's theorem. Suppose the contrary. That is del P over del X plus del Q over del Y, change sign. In U.